In this video, we're going to discuss electronegativity and overall polarity for a molecule that's covalently bonded. And this is something we can determine after we know its Lewis dot structure and three-dimensional geometry. I'm going to introduce a new periodic trend. It's kind of similar to ionization energy, and it's called electronegativity. And it's a measure of an atom's attraction for an electron. I kind of think of it as the opposite of ionization energy, or similar to it. Ionization energy measures how reluctant an atom would be to lose an electron, how much energy it would take to rip one off. And so this kind of mirrors it in that something like fluorine that has a very high ionization energy that does not want to lose an electron will also have our highest electronegativity. Some people also think of electronegativity as like greediness for electrons, if that helps. This is the electronegativity chart presented in your textbook, and it is the one that I will refer to and use. This is not the only electronegativity chart, and people disagree on these electronegativity values. They're determined experimentally, and they are all relative to fluorine, but there's a number of techniques that can determine them. And so there are a few of these that I kind of disagree with, like bromine and sulfur. I think they're more electronegative than this table leads us to believe. But I'll lean on this for this course. Just know this is something where if you are searching online, you might come up with different values for electronegativity. And you can see I've abbreviated a lot of the periodic table, or your text did, but we have our highest electronegativity here at fluorine, and our lowest down here around potassium and rubidium. And so we'll typically be working here in this portion of the periodic table where we have our metalloids and nonmetals that are more likely to form covalent bonds. And we'll use these electronegativities comparatively to determine how evenly electrons are shared within a covalent bond. So if we have two atoms that are bonded together that are the same, they'll have the same electronegativity. So two different carbons bonded together will have a bond that evenly shares electrons. And that's because each carbon atom that's sharing these two electrons right here has that same electron greed or electronegativity. So they'll pull at them equally, and so they'll be shared evenly. When we have evenly shared electrons in a polar bond, we call it nonpolar. Sorry, in a covalent bond. If we have two atoms that are bonded together that are sharing electrons that have different electronegativities, then there's a possibility that will uneven sharing of electrons from those different electronegativities would create a kind of uneven distribution of electrons. And the way we determine if that's happening is by comparing the electronegativity values of the two elements that are bonded together. So here's carbon and hydrogen bonded together, sharing two electrons. And carbon is more electronegative than hydrogen. It'll be able to pull electrons to it more than hydrogen will. And so we compare this difference between the two just by taking the difference, literally subtracting them. So 2.5 minus 2.1 gives me 0.4. So I have an electronegativity difference of 0.4. Now, slight changes in electronegativity will give us electrons that are maybe not shared perfectly equally, but it's kind of close enough. It doesn't create too much of a disturbance in how those electrons are distributed. And so this is actually our upper boundary here. If we have a 0.4 electronegativity difference, we still consider this a nonpolar bond between the carbon and the hydrogen. They're shared evenly enough. And so this will still be nonpolar. Now, if we have an electronegativity difference between our two atoms, like carbon and oxygen, that's larger than 0.4, so 0 to 0.4 will be nonpolar. If it's greater than that, if it's 0.5 all the way up to 1.9, then we consider this something called polar. Which means that the electrons really are not shared evenly. So if we look at carbon and oxygen, carbon has a electronegativity of 2.5, and oxygen has an electronegativity value of 3.5. So that difference is our 3.5 minus 2.5, which equals 1.0. So it falls in this range right here of 0.5 to 1.9. And so we consider this a polar bond between the carbon and the oxygen. This means that the electrons are not evenly shared between them. They're pulled more towards the oxygen than the carbon, which you can kind of imagine it as being like an electron cloud that just is disproportionately around that oxygen compared to the carbon. So there's just more room around there. And we represent this in a couple ways. We can represent it with what we call delta plus and delta minus symbols, or partial negative and partial positive symbols. If you use these, you need to make sure you use both. So you put a partial negative symbol right by the more electric negative element, and a partial positive charge by the element that's less electronegative. Another way to represent this kind of disproportionate electron sharing is with a dipole arrow. I think this is a little bit easier. So if I have a carbon-oxygen bond that I'm trying to represent is polar, or that is not sharing electrons very evenly, I use a dipole arrow like this. And the trick is that the arrow points to the more electronegative element, and this positive symbol is near the less electronegative element. And that indicates that electrons are more likely to accumulate near the oxygen rather than the carbon. So here's that summary of those boundary points. If anything is less than 0.5, then it'll be nonpolar and the electrons are evenly shared. Anything that is 0.5 to 1.9 will be polar covalent, and the electrons will be unequally shared. They'll pull more towards one element than the other. And then if it's a greater difference than 1.9 units, then we actually have an ionic compound. The electrons will be so much more attracted to one than the other that they'll actually transfer through a redox reaction from the less electronegative element to the more electronegative element. And you would get something like sodium chloride. An example of that polar covalent is something with a carbon-oxygen bond, and our nonpolar ones would be something like a carbon-hydrogen bond. So that is the polarity of a single bond. And we only show that it's polar or use the dipole arrow if it's actually has that electronegativity difference greater of 0.5 or greater. But we can also assess the polarity of an overall molecule. And that is kind of what we've been building up to. Polar molecules will dissolve in water, whereas nonpolar molecules will instead dissolve in something like fat. And so now we've got this difference that we can directly determine from just a structure of from a chemical formula. And then we have information about how it'll behave in the body, whether it's water soluble or fat soluble, which is pretty powerful. So now we have to figure this out for the entire molecule. And the first step is to identify your polar bonds and then assess if they all pull in opposite directions and cancel out. So here's an example. We've got our CH2O, and we just have one polar bond. It's between the carbon and the oxygen atom. And so there's nothing else happening in this molecule. And so we're going to see a disproportionate amount of electron density on this end of the molecule. And so this will be an overall polar molecule. If I had something like boron trifluoride, then I actually have 3 polar bonds. And I'm going to have electron density from each of these bonds disproportionately at the fluorines. So while I have these polar bonds, this disproportionate fluorine like attraction to the electrons, or the disproportionate collection of electrons around the fluorines, is evenly spaced out 120 degrees apart from one another. And so if you look at the overall electron density of the molecule, it evens out. And so this is non-polar, even though you have polar bonds. I like to think of these as the dipole moments cancel out. That if you added them up, like if you did some vector math and you added up all of these dipole moments, they would equal 0. Let's look at another one that has 3 polar bonds. Let's look at NH3, and those nitrogen-hydrogen bonds are all polar. But there's this electron cloud from the lone pair that pushes all of these nitrogen-hydrogen bonds down. And so we don't have this trigonal planar geometry we had for our BF3, which means that these dipole moments don't actually cancel out. Some of them do, but some of them reinforce each other, and we get this overall dipole moment that's going up here. And so if we have a lone pair, in situations with a lone pair, we're going to see that we have polar molecules if we have polar bonds. Another example where that happens, but without a lone pair, is if we have some non-polar bonds and some polar bonds. In this case, we're going to have more of our electron density gathered by the chlorines, and the hydrogens are going to be just like a lone pair. They're not going to cancel out that pole, and so we get this net dipole moment that goes in between our 2 polar bonds, and we have a polar molecule. Give this problem a try. I'll go over the solutions to this one as well as this one in a following video.